Okay, any question about the previous session? Today we want to continue our discussion about GANs, Generative Adversarial Nets. We see that there is an intuition that if you rely on likelihood, you will have a very maybe unreliable metric to fit your model. Why? Because we see that the model likelihood for a garbage model is bounded using these two numbers. This is the data likelihood, the best achievable one, and this is the upper one, and this is the lower one. It means that it is bounded by these two numbers. But there is another point that if the dimension increases, the data likelihood will also be increased linearly with the dimension. In other words, if you are working with CFAR 10 dataset, then the garbage model likelihood typically is bounded by these two numbers. It is between minus 1000.61 and minus 1000 here. But by increasing the dimension, because the likelihood, the data likelihood, the true data set likelihood is also increased, the absolute value I mean, your model likelihood is to some extent sandwiched between these two numbers. In other words, a bit improvement in model likelihood is very considerable, and a bit improvement in these numbers is maybe unreliable. So we want to think of something else or other than the likelihood. Or equivalently, we want to have some metrics that fit the model in a likelihood-free manner. So this was the intuition behind the fact that why we are looking to get maybe rid of the likelihood for distance metric. Okay, so we see that there are some models that have great likelihood and poor samples, and also there are some, this is the great likelihood and poor sample, and there are also some models that have poor likelihood and great samples. What was that model that on the opposite side? In which condition your model has great samples but poor likelihood? Yeah, a model that is overfitted to the training data or memorized the training data. That model has great samples because it generates the training data, but on the other hand, it has a poor likelihood because it cannot generalize this to data set other than training data. So we want to have some new distance metric. Oh, here, about your questions in the previous session. You know, here we want something, we want the minimization over a distribution so that the minimizer of the distance metric is again the data distribution. It means that the best option for you in terms of minimizing your divergence is data. If you reach your minimizer of your objective, you are sure that it's the data distribution, you know? This is the objective. This is not what happened. This is our objective. We want to design a distance such that this equality holds.
So we want to find a distribution called P.
Exactly.
That the divergence between the actual distribution and our distribution is minimized.
Yeah, and the one that minimizes this divergence globally is again data.
So you mean that P and P data are equal? Because we
it means that the minimizer, it means that this is the minimizer of the divergence. The divergence is minimized when the two inputs are equal.
Exactly.
Yeah. And this is a great objective because when you reach it, you are sure that you are in the best point. Yeah.
So is there any cases that like P and P data does not have like zero divergence?
Yeah.
So in this case, they are not equal. So this is not P data; it's just P.
Yeah, it does not mean that the value is, what is the value, okay? The minimizer, whatever the minimizer is, other than 0, the minimizer happens when the distribution you are looking for is exactly the data distribution. Yeah. Okay. So we want to look for something like this, but we want to constrain ourselves to the cases of likelihood-free metrics. This is the objective. So we want to design the divergence. Okay. So we want the first part in the GANs to reach the object to achieve our objective is designing a generator. The generator is a model or a neural network characterized by, it has a latent random variable z. We are interested in latent variable because latent variable may encode attributes. Latent variable can be used for downstream tasks, for example, classification or other tasks. Okay, and a generator network G theta, which is from the dimension m. Here it was better to write d, the dimension we observe. So because we just want samples of p theta, we want to be likelihood free. So there is no limitation over G mapping. So the first, you get rid of something that you need to be in a distribution. For example, in the approximate posterior, in the VAE, in the output of your amortized network, you do not generate samples from the distribution. You are limited, you are constrained to generate the parameter of your distribution, your posterior, approximate posterior. Here, you get rid of this limitation, and you design a network. This network, when input with Z, generates samples X, and you know that this X are coming from an distribution, and you do not exactly access to this distribution. You just have a generator, and the generator is capable of generating samples of that distribution. And you do not, you want to design your metric such that you do not need to explicitly know the model the distribution. You just have a generator. The generator just can generate samples of the distribution. So we are likelihood free. Okay, so this is the demonstration of the generator. The generator inputs with a latent variable z and generates samples from a distribution p theta of x, but we do not have explicit access to this distribution. We just have these x vectors. Okay. So now we want to design that divergence. Okay, pay attention how we design the divergence. First, we have samples because we want to design the metric based on samples. So we have samples from both data distribution, they are easily the dataset samples, and model distribution. What are the model distribution samples here? This generator can generate samples of that kind. So we put them together and generate a label dataset. How? I assign a label yi to each of these xi's. Each of these xi's comes from either your model or your data. If the data is coming from the data distribution, I label it as 1. And if it is coming from the model distribution, I label it as 0. So I have a label dataset as this dataset. But pay attention that this dataset is a function of generator, because if the parameter of your generator changes, these xi samples will be changed. So you have a dataset, you have a labeled dataset as a function of the generator parameters. I made a dataset labeled how? By discriminating between data coming from model and data coming from the data distribution. Okay, now I want to design the distance metric. Pay attention how the distance metric is designed. To narrow our selection for the divergence metric D, we assume it to be a classifier that models the marginal distribution over labels given the data. And how we model it? We model it with a Bernoulli. Why Bernoulli? Because it is a 0 or 1 classification problem. We model it by a Bernoulli distribution over Y given a function that we call it discriminator function and characterized by this parameters phi. So what happened here? You have an input vector X and you have a discriminator network D. Now you have a classification problem. Assume we have a classification problem, and in each classification problem you want to model the conditional distribution over your label given the data. How you model it? You model it by this Bernoulli distribution. Why Bernoulli? Because Y is binary. And the discriminator is a function that when you input X and pass it through this discriminator function, it generates the parameter of that Bernoulli distribution. It means that if the output of this discriminator is near 1, it is more probable that the data X is coming from, it is near 1. So it's probable that it's coming from the data distribution. If the discriminator outputs something near 0, it means that the data is probably coming from the model distribution. Okay, so the discriminator plays an important role. It can discriminate between data coming from the model distribution or data distribution, and we claim that this discriminator can be a distance metric. But how? So for Bernoulli distribution, we know that we are modeling the distribution over Y given X by Bernoulli, and you know that a Bernoulli distribution, pay attention to the simple case of Bernoulli. We know that Bernoulli over Y given a parameter lambda was modeled as this. Lambda to the power of Y minus 1 minus lambda to the power of 1 minus Y. This is a simplest and a more compact way of writing the distribution as this notation. This is compact form of this two cases distribution. So just I replace lambda with d phi of x. So this is the distribution over Y. So we can write the cross entropy. This is exactly a classification problem. There is nothing else than classification. In the classification, you again maximize, the maximization is not written here, but you maximize the log likelihood of your label given your data over the joint distribution. I just write down this expectation using total expectation trick. So that for the class Y, you have this expectation, for the class 0, you have this expectation, and we know that when Y equals to 1, pay attention that we have this prior information that your data set is balanced. It means that the data coming from the data distribution and your model distribution are equal with equal probability, and thus you can simplify the expectation as follows. P of Y equal 1 is 1 over 2. The expectation of X given Y. What is this distribution? What is this distribution? The distribution over X if the label is 1. Pay attention to our previous. If the label is 1, you know that data are coming from the true data distribution. So I just replace it. If data is coming from the label 1, the data is coming from the true data distribution. The logarithm of this value is written here. You know that I replace y equal to 1 in this formula, and I reach the log of the discriminator. Again, for the probability of y equal to 0, we have again 1/2 probability, and the expectation over x with label 0. What are these x's? Where are they coming from? From the model. They are coming from the model. So I write down x coming from the model distribution, and again the log of p phi with for y equal to 0, I replace y equal to 0 here. So this term will be eliminated, and we have just this term to the power of 1, so I replace it here. So the loss of classification for our generated data set is this loss. Now we want to claim that this loss can be a divergence for our generative model. Is it clear till now? What happened? Let me recap. In the case of GAN, previously we just have the logarithm of the model distribution over your data, and you have an average over your training data and maximize it. We call it maximum likelihood estimation, and we know that it is equivalent to minimizing the KL between the model distribution and data distribution. We apply it in different cases. Autoregressive model, we applied in VAE. VAE does not apply to the likelihood directly, it applies to the lower bound. But it is not different because you're again working with likelihood. And also we use it for flu model. In all of them, you work with this loss. But now what happened, we see that likelihood, we have some models, we have some p theta of x that has great likelihood but poor samples. What was the sample? What was the distribution that has this property? Great likelihood, poor sample. The one that we generate with 0.1 of the data and plus 0.99 of the noise. Do you remember that this model has great likelihood? Why? Because the likelihood is sandwiched between the model, the data likelihood, and when the dimension increases, it was more and more sandwiched. Okay? But it has poor samples because in 1% it has great sample, in 99% it generates noise. So we have this limited, and also on the other hand, p theta of x with great samples and poor likelihood. What was that kind? Great samples, poor likelihood. How? Overfitting, exactly. When the data was overfitted, you have great samples because it generates your training data while it has poor likelihood. Why? Because it cannot be generalized. It is overfitted to the training data. Then we think of some metrics other than likelihood. How? We want to have a distance metric between distributions such that if you have samples from them, then you can calculate the divergence. So we design a generator. The input to the generator is z coming from a standard normal, for example, 0 and I. And the output are samples from a model. We do not know the model explicitly, but there is a model and these samples are coming from that model. So our objective is met. Why? Because I can fit this generator with samples from a standard normal and have samples that is needed to calculate the divergence. Okay? Also, I can easily sample the true data distribution. How? By sampling the data set, by taking samples of the data set. They are coming from the true data distribution. So what happened next? I start to generate a labeled data set. How the data set is labeled? The data set is labeled from the origin of the generation. Is the data coming from the data or the model? Which of them? If the data is coming from the true data distribution, here, this item, you will label it as 1. If it's coming from the model distribution, you label it as 0. I put them together and generate a new data set, labeled data set. We do not face labeled data set in generative modeling till now, unless the conditional generation. Here is just a trick to show how our divergence is produced. Okay, it is just a trick. It is not what happened in practice. Okay, and what is the distance metric? Now I claim that a classifier of this distribution can work as the divergence between the generative model you design and the true data distribution. This is the key point. If I design a classifier for this data set, equivalently I design a divergence metric between the data distribution and model distribution. Pay attention to this point. This is the critical point of GANs. It shows that the divergence is equivalent to a classifier for the data set you generated. Okay? So we know that the classification loss is, this is just the classification part. It is, you have seen this part previously, but maybe in other notations. It is nothing other than a classification problem, and the resulting loss, this is your classification loss. We do not have anything with the generation yet. Okay? But you see some intuition of your generative, your data, true data and model data here. One term is based on true data distribution and one term is based on model distribution. And we know that why happened, yes.
So I still don't get the critical point. If you minimize, if you maximize that likelihood for that expression,
yeah,
how I think what you'll end up with in the end is you'll just be able to tell with good accuracy whether something belongs to the data distribution or the generative distribution.
Oh, yeah.
How is that?
You do not take the connection between this loss and generative the divergence, yeah?
Yeah.
Okay. We will focus on this part, I think, more. Yeah. Let's continue this, and then you can easily see that how it can be used as the divergence for generative modeling. Okay. So just pay attention that this is just the classification. You get the classification part. Do not pay attention to the divergence we were looking for. Just this is the loss for the classification of the data set we generate, we produce. I do not want to use generate as you may confuse it with generative model. Okay. So if I'm let's work on the classification. In each classification, you know that you want to maximize the likelihood, your conditional likelihood. So I add the maximize of the loss here. So I want to look for the best, let's say, discriminator. Okay. So let's see what happened here. If the data distribution, if the model distribution equals the data, what happened for this loss? Then the samples are inseparable. What does it mean? Assume that you reach a point where the generative model is it is generating samples which is coming from the model distribution, but the parameters are such that the model distribution is exactly the data distribution. It is maybe it happens in practice, okay? So when we have this case, what happened to your discriminator? Your discriminator wants to discriminate two types of samples, okay? Y equals to 1 if x coming from the data and 0 if x coming from the model, okay? What happens if the data and model are exactly matched? How the discriminator can separate samples that are coming from exactly the same distribution? We assume that these two distributions are exactly the same. So there is no information in X so that you can infer Y from that information. But because all X's are coming from the same distributions. So what happened to your model, to your discriminator, to your classification problem? Pay attention to the classification part, not the generative. Because the samples are inseparable, your discriminator always outputs 0.5. This is the best value it can output when they are matched. It can be shown that why this is the best value. If you have any problem with this discriminator rule, we can talk more about this at the end of the class. So when you have matched the distribution, then you have the best classifier, the best discriminator is this discriminator that outputs 0.5 for each input, irrespective of the input. So in this case, your this divergence, the divergence you design here, is simplified because each of these terms equals 0.5. You have 2 times log of 0.5. But what happened if there is any type of discrepancy between the model and the data? What happened? An ideal classifier, pay attention to the ideal part. An ideal classifier, if there is any discrepancy between these two distributions, the most powerful discriminator can easily understand that discrepancy. And so that it can output the true labels when you input or pass X through the discriminator. So what happened next? What happened is that you have the divergence equal to 0. Pay attention to these two parts. When they are equal, you have this value. When they are not equal, for the case of ideal classifier, you have 0. So it can be considered. Why? Because the minimizer happens when they are matched. Is it clear how we designed this divergence? Yes.
0 is not clear.
0?
Yeah.
This part?
Yes.
You know, when you have exactly the labels, if you put it here, you have always, for this part, you have log of 1. For this part, again, you have log of 1. Both of them are constant 0. You know, because X is coming from the data, okay? It outputs the true label. The true label is 1. What is the log of 1 is 0. So it go out and the logarithm of a constant is 1. The expectation of a constant is 1. Also for the data coming from the model distribution, it outputs 0. 1 minus 0 is 1. The logarithm of 1 is 0. So again you have 0.
So this d phi of x, is there a probability?
It outputs the parameter of the Bernoulli.
Outputs the parameter.
Yeah. It outputs a value between 0 and 1. Yeah.
So when the p theta and p data are not matched, so the output of the Bernoulli would change based on each input.
Yeah. No. Pay attention to this term, the ideal classifier.
Okay.
The best classifier you can ever imagine. What happened when they have discrepancy? If you have the most powerful classifier, it can understand they are not matched. So it outputs 0, exactly 0 for data coming from the model distribution and exactly 1. This is ideal. everything is based on the ideal classifier, but we know that in practice it does not happen. But it is just the justification for the divergence we are working with.
Okay, so for each input as x, okay, we will have different label as y.
Yeah.
Okay, so per input we will have different Bernoulli parameters.
No, I mean that because it is ideal and because they are not matched, it can exactly output 1 for data if x is coming from the data distribution, and 0 if it is coming from the
So, like following what I said, per input, whether it's from data or whether it's from our distribution, it will have different Bernoulli parameter as 1 or 0.
Yes, exactly.
So it's just like a set of a classifier that for each input, it has different parameter.
For each input, it outputs either 1 or 0.
Either 1 or 0. And like this is not realistic at all.
Yes, it is not realistic, yes. Yes, it is not realistic, but you will see that the justification in the GAN paper, to show that what is exactly their divergence is exactly based on this assumption that we have an ideal classifier. But what happened, we do not have an ideal classifier or an ideal discriminator, but everything works in practice. It means that it can capture the data distribution. So the maximize of this loss, the maximize of this likelihood, is the likelihood. The maximize of this likelihood can be a divergence. And what is important with this metric, in contrast to the previous 3 generative models we reviewed? This metric is likelihood free. You do not see, you cannot see any p theta of x. You know, by just having samples of these 2 distributions, you can calculate it. So it is likelihood free. It is the important part that we start with. Okay, let's continue. Again, pay attention to the fact that the optimum classifier is a function of theta. I previously emphasized that the data set you have generated is also a function of the generator parameters theta. So the resulting discriminator, the base discriminator, is also a function of the theta parameters. So just pay attention to the fact that if you maximize this term for a generator, the resulting discriminator function is also a function of the generator parameters. It's maybe, yeah.
Would you please go back to this? So still I don't get this connection of the divergence metric and the maximization on the right-hand side. So you claim that this the distance metric is equal to this maximization, and you have 2 different values for the distance metric. So what? For the distance?
Yeah, you know, what is this value? This is a negative value.
Yes.
And the minimizer of this loss. Okay? It means that consider this complete term, maximum of that term, as a discriminant, as a discrepancy, as a divergence metric. It said that for this divergence metric, when the distributions matched, you have this value, which is a negative value, and it cannot be less than this value, this function. We know that the random classifier has the minimum value. On the other hand, if there is any discrepancy, it will be increased. What we were looking for something, exactly the optimization you have questions about in the previous session. We want the minimization over the distribution of a divergence metric between the data and this, so that the minimizer is again the data. This is the option. Yes? This is exactly the option, because when you have your model is exactly data, you reach the minimum. And if there is any discrepancy, if an ideal classifier outputs 0, which is higher than this value. So it can be a candidate for this divergence. Yes?
And for the maximization inside over phi.
Yes.
Like we want to minimize this whole maximization over the p. This is the argument.
Yes. We will talk about that later. Yeah.
And the phi that we want to maximize is like acceptable when we have d phi of x around 0.5 when the two distribution matches.
Yes, exactly. Any question? Okay, we maybe find a divergence. And just here I want to point it out that if you haven't assume the data set is static, the resulting phi is a function of the generator parameters. So pay attention to that part. Let's recap, and based on our initial viewpoint to generative model, okay? We start with this idea that there is complete set of possible distributions over the data with dimension d, and your data distribution is 1 point over this space. Then you want to characterize a family, find this red set. So here, which part design this set, this family for you? Who is responsible to characterize the family here in the GAN? The generator. The generator does not explicitly it does not model it does not model a model, provide you with a distribution over the model, but it generates, not this part, it generates samples for you. It means that when you change the parameters of your generator, you are working with another distribution. And by changing the parameter of the generator, you are moving in this space, in this subset. Okay? So the generator is the one who is responsible to produce this set. It means that if you take a more powerful generator, you can cover a larger space. Is it clear? Okay. What is this loss? This distance metric? The distance metric is exactly what we found. The maximum over phi of the classification likelihood, marginal likelihood. Okay? So we characterize the family, we characterize the loss. Just we should minimize the loss over the model distribution to find the best model. It is exactly similar to the models we see before. Is it clear?
Wait, so if you have the ideal the discriminator, then the loss is bounded between 0 and 2 times log of 0.5, right?
Yeah.
Okay.
This is the minimum. This is the minimum value. This is the max.
If you have ideal classifier.
Yes, if you have ideal classifier, yes. Yes?
So this is a distance metric, so it has to hold up to triangle inequality and symmetry.
No. I do not. Maybe I in a wrong way. It is not a distance metric. This is a divergence. But we use it to compare the model and the data, like data distribution. Yeah, it is not a distance. It cannot hold those inequalities. Because it's much more complex than something like maximal likelihood.
So in this divergence metric, is all that we're seeing that it minimizes, or it hits 0 when it's ideal, and then it's not 0 when it's not ideal, and I guess the question is, why are we, like more formally, why is this the metric we're using?
Yeah, this is just the first. Justification behind GAN. We will see another justification in the next session, but again based on this assumption, ideal classifier. Without ideal classifier, you cannot find a very, let's say, intuitive justification for GANs. But here, what happened? I said that there is this divergence. This divergence reaches its minimum when the distribution matched. And it is higher than its minimum when the distribution does not match with assumption. So it can be a divergence. Because if I found the minimizer, I am sure that I am in the best place. The monotonical property may be also included here. But you can see that in the next justification how it can be connected to likelihood and KL divergence. Yes. Any question?
Like it's maybe a silly question, but
No.
why don't we do this for like VAE, AR, or FM, like be probabilistic independent?
Here we are escaping the likelihood, but the likelihood has some interesting properties too. Why? For example, if you want to monitor your generative model, likelihood is a great option because you can easily calculate it over your validation set. But when you are working with this type of information, this type of divergence metric, they cannot be used for, you will see how you can monitor the qualification, how you can qualify them. But they have some major problems with monitoring the training. Yeah. So this is the trade-off. Okay. Any question? Yes.
It sounds like you need to constrain this model so that it ensures that the individual components are approaching 0.5, or by default it's going to approach it.
No, we do not monitor the value of the loss anymore. This is just a justification for understand that this can be this divergence. Yeah.
So this is just like the theory.
Yeah, this is just because the ideal classifier is also impossible assumption. Yeah.
So my problem with this, at least the first part, is that you can still end up in a position where you have that loss being twice low, 0.5, right?
If you are at that point, it means that you recover the data distribution.
Okay, let me think.
Assume that the classifier is ideal, Pay attention. I think I have the critic viewpoint. This is also another great idea to look at the another viewpoint to GANs. DP can be seen as a critic who is criticizing the G theta performance. This is another viewpoint to the problem. You have a critic. The critic is looking on what you are doing. The critic has access to the samples from your training data, and then look how you are generating data. This critic, if it is the most powerful critic ever you can find, can easily understand the minimum discrepancy or the minimum divergence between your performance and the data set. What happens when it understands? It can easily say that this data is coming from your model distribution and this data is coming from the data distribution. So you reach the 0 point, the zero value of loss. But assume that you again employ the best critic for your task, and that critic cannot understand each data is coming from the data distribution or model distribution. This is the best point. The classifier is implementing that critic. That critic, and when you maximize the classification likelihood, it means that you are employing the best critic. The best classifier cannot understand whether the data is coming from the data distribution or model distribution. Okay, let's just finalize this figure. So we understand that what is the distance, what is the loss. We want to minimize this loss. We want to minimize this loss because we know that if we have an optimum, if we have the most powerful discriminator, the minimizer of this term is the place that your model distribution is exactly the data distribution. So this is the problem. The problem is minimization over the generator parameters of the maximization over the discriminator parameters of this V function, and the V is designed as we previously see. This is the conditional likelihood of labels given X. So we design the metric. Okay. The above approach to create a generative model is called generative adversarial net. This is exactly GAN networks or nets. This is exactly the GAN. The target is to train a generative model. The focus is on the generation task. So here we do not have, we are likelihood free. So calculating the likelihood as one of the tasks that we look for in generative modeling is not, maybe not important here. You just want to have a model that can generate samples. The generator and discriminator are opposing each other, so they are adversarial. The justification for adversarial is the fact that, again, pay attention to that critic. The critic and you are opponent. It means that you generate something, and the critic wants to understand that is it the data is generated by you or it is coming from the training data. So we have some adversarial gain between these two parts, and both generator and discriminator are implemented using neural networks. So the justification for nets. So you have generative adversarial nets. Okay. This is the critic viewpoint that we talked about before, and this is the final architecture. You have a discriminator. The discriminator is here. It inputs samples coming from the data distribution and also samples coming from your model distribution, and it can assign a value to each of the data. If the value is near 0, it means that the discriminator understands that the data is, predict that the data is coming from the model distribution, and if it is near 1, it is coming from the data distribution. Okay. This global optimality talk about another justification to GAN, and here you can easily, you may understand a better justification about the GAN. So let's talk about this new justification. For this new justification, the first claim is that for a fixed generative model, the optimal discriminator is this discriminator. I think you will solve it in your homework, but it is also written in the paper how you can understand that. Assume that the generative part is fixed. You do not want to change the generator. For a fixed generator, the optimal discriminator is this discriminator. For this optimal discriminator, you can see y when they are exactly matched, it outputs 0.5. Okay? This is the optimal discriminator. But the optimal discriminator is again with the assumption that you can design the discriminator arbitrarily. It means that there is not a neural network named D, and the discriminator is implemented using this function because you want complete freedom. It means that you want to assign exactly this function to your discriminator. So again, you assume you do not have any constraint over your discriminator. So it is not applicable to what implemented finally in the GAN. But assume that you are free here as the complexity, and you can design discriminator exactly similar to this function. Now, this is exactly similar to the assumption of ideal discriminator. Okay, in the previous part we see ideal discriminator. Here we see that we assume that the discriminator can be this function, but in practice it cannot be, because it is limited to the function that can be implemented using your neural net here. Okay, but assume that we can do that. So here I just talk about the limitation that in practice you cannot apply this equality. Now let's recap what we have in V. V was assume that C theta is the maximization of V over phi. It means that we do not have the minimization over theta here. So so C is a function of theta. For every theta you have a different C. This is because we assume the generator to be fixed. So if I replace the discriminator with the optimal discriminator, I can omit the maximization, because that's the optimal discriminator. So you do not need to have the maximization anymore, and this D star is the optimal value here. I just rewrite the formulation of D star as we have here in the formulation of V, and we reach this point. Okay. This C theta is known as virtual training criterion. Why? Because this C theta is not achievable by you. You cannot design or use D star here, because D star needs freedom here, but you are limited to neural networks here. So we cannot achieve this C theta. But just for the justification and as a virtual training criterion, assume that we have C theta. So we want to minimize this C theta. Okay, this GAN is a likelihood-free model. Equivalently, we have expressions to calculate p theta. Thus, in practice, you cannot calculate or approximate the virtual training criteria, as we talked about before. You cannot implement this virtual criteria, but you can work with this virtual training criterion. How? Here, this is the original formulation. This is just adding plus and minus a term to the objective function, and this term is to cancel what you have added. And if you pay attention to this loss, the C theta is the KL divergence between the P data, your true data distribution, and this mixed distribution, and also the KL divergence between P theta and this mixed distribution. This definition, we have seen in the start of the term that this definition, the summation of these two KL divergence is the Jensen-Shannon divergence between two distributions. JST obey the maybe I think JST obey the let's say it is a JST of P data and P theta is equal to P theta and P data. But it does not have triangular property. What happened? Your virtual criteria is something which is a function of the distance or divergence between the distributions. This is another justification. It means that assume that you have a discriminator that can be equal to D star. This is not possible, but assume that we are in the case that you can design this D star. If you design this D star, you have a term C theta, and you should minimize this C theta. But this C theta, although it is based on likelihood-free formulation, it is equivalent to 2 times the JST between the true data distribution and your model distribution minus a constant term. What happened? This is a new justification. In this new justification, we can easily understand why GAN work in practice. Is it clear how it is converted from the formulation of V to this C? So the virtual training is 2 times the JST minus log of 4. And keep in mind that the JST is non-negative, C theta is greater or equal to minus log of 4. Again, this is not what happened in practice. Why? Because the star cannot be attained. Okay? It is just a justification why the GANs can work in practice. Any question? Okay, and we know that if you design the theta such that these two distributions matched, it means that you change theta such that they match, the JST equals to 0, because JST is 0 when the distributions matched, and then C theta equals minus log of 4. So the minimizer of C theta is minus log of 4. Thus, P theta equals to P theta is the global optimizer of C theta, because it is global optimizer of JST or these two KS. Is it clear? Any question? So let's think of the training algorithm and how we can train GANs. Pay attention that we start with something which is likelihood free. And we end with C theta, which is 2 times JST of P theta and P data minus log of 4. What happened? Starting with something which is likelihood free, we are implicitly minimizing the distance between the distributions, but we do not have the direct access to the distributions. We just have access to the training, to the samples from the distributions. And here you can see that how you can train GAN using just samples. You see the objective of GAN is this objective. So how we train it? How we can calculate this expectation? Monte Carlo estimation. Because you have samples of this distribution. What are the samples of data? They are your training data set. What are samples of P theta? Yeah, samples from the generator. Exactly. So what happened? We have access to 2 sets of samples, Z coming from the prior. We have a prior over Z. This is that prior. We have these 2 sets of samples. What happened next? You estimate V theta and phi using the Monte Carlo estimation. We know that the Monte Carlo estimation for this expectation is the average of this value over the samples coming from the data distribution. Exactly, I write it here. And also expectation over the data coming from the model distribution. Instead of x, I write down g theta of zi. We know that g theta of zi is xi, which is coming from the model distribution. Yes? Is it clear? So I have a term as a function of the model and discriminator parameters and generator parameters. So you can calculate this term as a function of these 2 sets of parameters and then maximize it with respect to phi and minimize it with respect to theta and train your model. We know that this is different from what we have seen in the previous part as C theta, and also what we have seen in the start of the discussion about the GAN, because the discriminator is not ideal. The discriminator has not arbitrary freedom. So it cannot be design equal to D star. It cannot be an ideal discriminator. But in practice, when you optimize this V theta, it means that you minimize it with respect to theta, maximize it with respect to phi. You see that the generator is following the distribution of your data. Any question? Yes.
Do you do this in 2 steps?
Yeah, you maximize with respect to phi, you minimize with respect to theta. Yeah, it's very similar to VAE. Exactly, in that case, we have phi and theta. Phi was the approximate posterior, theta was the model parameters. Okay. This is the GAN learning algorithm. You start with training data, prior over Z, and this is the number of iterations. Initialize these 2 parameters, theta and phi, and for some steps, you do what happened? Yeah, this part you update phi. It means that you first update the discriminator and then update the generator part. There are lots of tricks how to achieve a good performance on GANs, because if you pay attention too much in each of them at the starting point, you may not converge to a great point. And also we will talk about the mode collapse problem in GANs at the end of this presentation. But this is not the only algorithm to train GAN. There are lots of variants of these algorithms. Any question? So let's think of a simple example that you can find it here. Assume that the dashed blue line, this dashed blue line is the discriminator, okay? And the data samples from coming from the true data distribution are dotted black line. It means that the black, this is the true data distribution, and you want to your samples, this Z, after passing through the generators, mimic these distributions. At this time, they are not similar because the most of the density is here, while the true data distribution has low density here. Okay. And the generative discriminator p theta is the solid green line. This is the generative distribution estimated using these samples. This is this green line. It is clear why it has a peak here, because the density of the data after passing through the generator are located in this point. So you have the maximum likelihood here for your generator. A is near convergence. B is updating the discriminator converging to this value. The steps from A to B, you update the discriminator using the optimal value. Here it is easy because you are using the formulation of the distributions. So you can easily put the discriminator to the optimal value. So this blue line is the optimal value to discriminate the black dots from the green line. This is the optimal. It means that you cannot have the better one for this generator. Okay. Then what happened? Then the generator updates itself. How? It tries to mimic the performance or the distribution of the true data distribution. So the peak is shifted toward the peak of your true data distribution. Again, you can update the discriminator such that it can discriminate between these two distributions. I mean the black dot and the green line. And finally, and hopefully, you will reach a point that the generator distribution is exactly the true data distribution. And at this point, the optimal discriminator is the discriminator that outputs 0.5 always. This is exactly what happened in GANs. It means that you start with the discriminator is updated so that it can discriminate the data between the true data and your model data. You see that this is the value of the Bernoulli distributions. For these places, it is near 0 because the data is more probable to come from the model distribution here, and here it is near 1 because data here is more probable to come from the data distribution. And at the end, when they match, it always outputs 0.5. Yes.
So in point B that said the discriminant converge to the D equals to that formula, wasn't it unrealistic that we can't achieve this formula?
Yes. Here it assumed that it considered the functional form of these distributions. The function you have exact. It means that instead of having implemented them using neural networks, it assumed that the data is a Gaussian distribution with mean and with variance, and then after the samples are passing through the generator, again you have a Gaussian distribution with mu, mean and covariance matrix, variance value. So because you have the functional form of the distributions, you can exactly select this value as the discriminator.
So we assume that we have the access to the distribution of data and the theta.
Yeah, this is just a simple part, you know. After that, you do not have the p theta anymore. You just have a generator.
Yes.
Yeah, you just have a generator that generates samples for you. Yeah, this is just a simple demonstration. It is not what happened in practice. Yeah, because you cannot use this value for the discriminator in practice. Yeah, but here, because they are simple, you can use that. But pay attention that the divergence is not using the information of the likelihood. The divergence is just based on the samples. The divergence is calculated based on these samples. It does not use the information of p data or p theta. You know?
So can you give me an example of how this D is calculated based on the sample?
Yeah, D not. I mean that you want to optimize the generator, okay? You have two-part optimization. Minimization with respect to theta and maximization with respect to phi. This part is unrealistic, as you said. But this part is based on samples. It's based on these samples and these samples. Just the samples are used to calculate and then update theta.
So in the maximization part, we have assumed that we know the P of data and P of theta at the same time.
Yes, yes. We use that information to have the discriminator equals to this ratio. This is unrealistic, but it can better visualize what happened in GANs. Okay, any question? And these are the samples generated in the first paper of GAN, which is huge improvements, especially for more complex images. This is the results for, let's say, the MNIST dataset. This is the result for TFD, face dataset. These are results for CIFAR10 dataset with the fully connected and a convolutional network. And these are the results in the original paper of GAN, but there are lots of work on GAN, and one of the most demonstrating papers that visualize great examples of GAN is is a paper that proposed deep convolutional GAN, DCGAN, is known as DCGAN. In that architecture, you have a generator architecture like this. This is exactly coming from this source. And the generator architecture in DCGAN input a vector in a 100-dimensional space. This is a normal distribution, standard normal distribution, and outputs a g theta of z, which is exactly the dimension of the images you want to model. The 64 by 64 by 3, it is a color image. And, and the discriminator here is a very simple discriminator, which is inputs the exact dimension of your images and then passing through some convolution layers, and finally you have a value which shows the parameter of the Bernoulli distribution. So what happened here? These are the samples generated using DCGAN. They are samples of bedrooms after one training pass through the dataset. Just one pass through the dataset, you have these samples, and when you increase your passes, it is the 5 passes, you will see some interesting images of bedrooms. And also another interesting property of GAN is the attribute vectors that we see before in VAE. It means that they can encode the attributes in their latent space. Again, similar to VAE, assume that I have, here it is a bit tricky because you do not have any method to calculate Z given X. If you have X, you cannot talk about Z. But for the case of our example, assume that first we have Z, and based on those Z, I generate X and observe that this is my image, okay? And also I have another Z, and when I pass it through the generator, I see that I have this image. So I call it this ZNW, it means that neutral woman. This is SW, smiling one, okay? So assume that I have access to Z. Then I can encode the Z of smile, the vector of a smile in the latent space. And if I add this latent vector of a smile into a neutral man, again, the neutral man is generated using this Z. It means that I have access to Z. I have a new Z, and hopefully, if it can encode the smile attribute, I expect this Z of Sm to be a smiling man. And as you can see, they are real examples in this paper. And as you can see, this is the smiling version of this man to some extent, which means that the Z of smile can efficiently encode smiling attribute in the latent space, exactly similar to VAE. But in VAE, we have another tool, which is the approximate posterior model, and that approximate posterior model can give you Z given X. But here, you have not seen any approach to calculate Z when you have access to X, and we will see it in the next session. So this is also another example of that smiling man. It means that you have these pairs, you have these groups. This group is a smiling woman, this is neutral woman, this is a neutral man. It means that when you subtract, everything is being done in Z space. If you subtract the Z value of neutral women from a smiling woman, you hopefully have the smile information in the resulting difference, and then you add that smile information to a neutral man, you will have a smiling man. This is exactly attribute detection. And also from other types of attributes, for example, this is the glasses. These columns are man with glasses, this is a man without glasses, this is women without glasses, and finally you have women with glasses. When you subtract man with glasses minus the man without glasses, you hopefully have the latent space information of glass.